Hey, we're going to get started with another video. This one is called, as you might be able to see, an Introduction to Limits. Let's get some of this stuff out of the way. Oh, and that's up there twice, but anyway, let's hope we're actually recording. I have two of those. It's going to freak me out if I don't do something about it. Which one is it? Let's get rid of that one. Alright, let's make sure this one's still showing. For record, so I want to keep going. Alright, so introduction to limits. Here we go. We'll get back to that picture in beautiful Island Pond, Vermont a little later. Hopefully we got the chance to talk about the nose and the fan as the reason that we want to have limits, know about limits. Not the only reason, but sort of a little piece. If we didn't, ask me about it. So, generally speaking, a couple of things on this page that we want to be familiar with. First of all, this notation. This, when we're writing it in shorthand, means the limit as x approaches 2 of this function right here, x squared plus 2, is. And when we've got a graph, we can sort of look at it. We can go, okay, as x approaches 2, where's this thing headed? Looks to be headed about there. What's that doing? God, it's crazy. Okay, about there, I would say. Other way is we can plug 2 in. 2 squared is, oh, so I'm way off, aren't I? 2 squared is 4. 4 plus 2 is 6. Let's try this again. Oh, yeah, it looks like it does actually hit up there at 6. I don't know what's going on with that part right there. It's going to change things. This thing is acting really weird. It might be a bad sign. So, plug in the number, get an answer. We're just looking for a y value. When we can see it on the graph or plug in a number, we are very happy. Okay, sometimes can't necessarily tell. We've got this piecewise function that we've talked about here. Piecewise function, looking for the limit. What we do when we've got a piecewise function is we just sort of trace along the graph. It really is about where we're headed, not where we're actually assigned to be. So as I head this way, it looks like we're heading towards 5. As I head towards this way, it looks like we're heading towards 5. So the limit is 5. Even though the function is defined at that point as a different value, the limit is 5, okay, and that tells us a little something that we'll talk about a little later about that function. Okay, so look at the function, and I know you can see this whole screen, so my little surprising thing is not that big a deal, but look at that function. Where are we going to have problems with this function? What's going to cause us to have some issues in terms of how this function behaves? I know what you're thinking. You're thinking, hey, if x is 2, that's going to be a problem. We're going to end up with 2 minus 2, which is 0, and that's not something we want to deal with. We can't divide by 0. So we want to know what happens to that function as we approach 2. So what's the limit as x approaches 2 of that particular function? Okay? So in order to do that at this point, we're just going to make a table of values. And we're just going to plug into that function, which is now on the next sheet, but you can see it. We're going to plug 1.5, 1.9, 1.99, 2.01, and 2.5 in a hopes that maybe it'll give us some clues about what that particular value is. What I'm going to do is I'm going to pause, give you a second to process those, and then when I turn this back on, I'll have the numbers all written in. Ready? See you in 2 seconds probably. All right, so we're back, and I filled in these numbers. Hopefully you maybe took a second to fill in the rest of them. So as we get closer and closer to 2, it looks like this function's getting closer and closer to 1. So we would say the limit as x approaches 2 of this function is 1. Okay, the y value that we couldn't find, because if we plugged in to the actual function, we get 2 minus 2, and actually the top turns out to 0, which is a whole other story for another day. Okay, so the limit is 1. Let's try another one. This one right here. If you take a second, you'll see that as x approaches 1, we're going to have a problem. 1 minus 1 is 0. 1 cubed minus 1 is 0. 0 over 0 is just not a good place for us to be. So we're going to do the same thing with the table of values. See what happens as we get closer and closer to 1 from both sides. See if there's a pattern. See if there's something that we look for, and work from there. You stop, plug those in, and I will be back with you in just a brief second. I know what you're thinking. It's like witchcraft. 1 second there's no numbers, the next second they're right there. So look at the pattern. Looks like in both directions we are getting closer and closer to 3, so much so that we would say that the limit of that function as x approaches 1 is 3. Going to look at that from a slightly different perspective, from the algebra perspective. Remember long division with polynomials? So if I would just wanted to rewrite x cubed minus 1 over x minus 1, that's like x cubed minus 1 divided by x minus 1. Real quick, long division. This number, we always look at the comparison between here and the first digit. So what do we need to multiply x by to get x cubed? X squared. X squared times x is x cubed. X squared times negative 1 is 1x squared. Subtract, boom, those are gone. 0 minus negative 1 is 1x squared. Bring down the next term, 0x. Need that as a placeholder. Go back to here. 1x squared divided by x is x. So I'm going to put plus x. Do the math. X times 1, x times x is x squared. X times negative 1 is negative 1x. Subtract. Boom. Gets 1x. Minus 1. Okay? Last time. Compare this to that. What do I need to multiply x by to get 1x? Why, it's 1. Okay? 1 times x is 1x. Minus 1. Subtract 0. Okay, this is really the equivalent of that other function, gotten the kind of long algebra division way. Now when I plug 1 in, which was our problem child, I get 1 and 1 and 1. As the Beatles said, is 3. Okay, 1 and 1 and 1 is 3, so another way to get there. We're not going to do long division algebra. Don't panic. Okay, sit down, relax. We'll be okay. Another example. Another problem. If I plug 0 in here, 0 plus 1 is 1, square root of 1 is 1, 1 minus 1 is 0. I get 0 on the bottom, I get 0 on the top. Trouble. Okay, we need to figure out what's going on. We're going to go to another table. You stop, I'll stop. We'll get back when we have some numbers here. Ready, go. Boom, there they are. So, where are we heading? 1.94, 1.99, 1.999. A little more than 2, a little less. So where do you think we're going? I'm thinking we're going to 2. Yeah, I almost wrote 2 excitedly, but then I realized that's 2 factorial, which is 2. So anyway, so if we can make a table of values, we can figure some things out, at least at this stage of the game. We'll get a little more sophisticated with this stuff as we move forward. Here we go. All right, we're going to do this one live in person. So as x goes to 0, we're going to have 0. The absolute value of 0, which is 0 over 0, 0 over 0, always a problem for us. So we're going to just make the table. If I take the absolute value of negative 0.5 and divide it by negative 0.5, I've got a positive on the top, divided by a negative, I end up with negative 1. Slow it down if you need to. Take the negative 0.1 absolute value on the top, the regular on the bottom, I get negative 1. Same thing here, negative 1. Go in the other direction. 0.5, absolute value divided by 0.5, that's 1. That's going to be 1. That's going to be 1. Okay? So, $1 million question. That's not the $1 million question. Don't show that message again. I ask you every day. But, $1 million question. What's the limit? I know what you're thinking, but no, it's not that. Okay? You were thinking 0. 0 sort of in between the two things, but that's kind of an arbitrary thing. Why not 0.2, point something, some other number in between the two? It's not the average of the ones. You know, we could clearly see on these previous ones that it was heading there. This is a big jump. So the answer is the limit does not exist. Okay, we're heading to 2 different places. In one direction, we're cruising along up here. The other direction, we're heading along there. There's a big gap. We can't just decide, oh, it's going to be here. No, we can't do that. So the limit does not exist. The reason, the function approaches different values from each direction. That's one of the reasons sometimes limits don't exist. We abbreviate it DNE, does not exist. There you have it. Cruising along now. How about here? What's going to happen as we get here? As x goes to 0, I'm going to get 1 over 0. Big problem. You know what this looks like, right? 1 over x squared. It's the volcano graph, right? I'm going to plug some numbers in as we go. Let's plug numbers in. 1 over a point over that. That's 4. That's 100. That's I don't know, 1 million, I think. Something like that. On this side, we get another 1 million. Okay, if I kept getting closer and closer to 0, like 0.0001, this number just keeps getting bigger and bigger and bigger and bigger and bigger, and we have some issues, right? You know what it looks like. You know what the graph looks like. Graph looks like this. like that. Oops, except we're supposed to stay on this side of the axis, but you know what I mean. It's that volcano graph. So what's the limit? The limit, once again, does not exist. Okay? Because we have what's called unbounded behavior. Okay? It's just there's nowhere where it actually is heading. It's heading off to wherever. So the limit does not exist. We've got unbounded behavior. Now we could have that same sort of thing if one's going up and the other's going down. We don't know what's going on. That's another reason limit does not exist. Okay? If you got your graphing calculator, take a second and graph this and see what happens. Make sure you're in radian mode. Your window wants to be pretty small, like between 0 and 1, and go. If you don't have it, here it is. Okay? It goes like this, and as we get closer to 0, this thing goes haywire. All this black thing, this black area here, it's just the thing bouncing up and down, up and down, up and down. If you zoomed in, it would be even worse and worse and worse and worse. So we get this oscillating behavior as we approach 0, and so the oscillating behavior is another reason why the limit doesn't exist. If we can't clearly see what's going on, we don't know what's going on. So, that's another reason why the limit does not exist. No matter how much I zoomed in, I'm going to get this same sort of looking graph right there. Okay? So, here we go. 3 reasons why limits fail to exist. If we approach different values from each side, boom, okay, whether it's that or that, we've got a gap, something like that, where the limit's not going to exist. Unbounded behavior, Zingo, like that, and oscillating behavior, you got the scribbly mess going on in the middle, that's a bad thing, okay? And typically, we tend to see this most often, followed by this, and we saw this already, and we'll probably never see it again, but it's fun to draw the picture, okay? So, wrapping up, the limit as x approaches c of a function is L. L is just some y value, that's all it is. Okay, sometimes it's pretty easy to find. Sometimes we can just plug a number in. I know I've got more time because I've been pausing, so I'm going to keep going. Sometimes we plug a number in and it gets there. Sometimes we can look at a graph and see where it is. Sometimes we can trace it along. Sometimes it takes a little more work. Okay, and we really didn't do a whole lot more work today. We just did some tables. We're going to get to the place where, today we did graphically. We did a little numeric where we plugged it in. When we get to this analytical stuff, that's the little more work stuff. Sometimes they just fail to exist. We want to be able to recognize that as well. Okay, so back to Island Pond, and tell me, why is that a limit? What represents in that particular picture a limit? Can't hear you, so you'll have to tell me tomorrow. Hey, thanks for watching. Hope you learned something. We'll see you soon. Oh, 13 minutes.